All right, thank you so much for coming. Welcome. Session check, if you're in the right room. I don't know, it was like a very long day. Very long day, so this is why you need to make sure that you're in the right room. So I'm going to be talking about a lot of things here. I'm going to be talking about some Kubernetes stuff, a little bit Kafka stuff, a little bit Kafka Streams, hodgepodge of different tools, and obviously I would love to hear some of the opinions and some of the feedback. So my name is Viktor. I'm a developer advocate at a company called Confluent, and in Confluent, it's what we do. We contribute a lot of things to open source, namely to Apache Kafka project. And we also build something on top of it. We build one of the distributions of Apache Kafka that we call the Confluent Platform. And also we build the managed service for Apache Kafka. If you need to use Apache Kafka in the cloud, the Confluent Cloud, this is the place to be. How many of you have Twitter here? Twitter, nice. I conveniently placed all the things that you need to know when you will tweeting. So hashtag swampUP, yep, hashtag swampUP, it's very important. And I would appreciate if you tag me there if you find something interesting to tweet from the session. Thank you. Another thing that you need to know about me, so I'm building a lot of things, specifically Hello World applications, and these days I cannot build anything less than highly scalable and highly available applications deployed in containers, through Artifactory, in Kubernetes, and all these kind of things. This is what I do. And today I will be showing some of the applications that, again, highly scalable, highly available. We'll try to do like a scale up, scale down, and see how it works and how it will appear and how it affects the processing thing. I want to say a few words of thanks to two amazing people. They both, the Gwen and Matthias, they work at Confluent as engineers, and they help a lot with this talk, and I gain a lot of inspiration from the work what they do. All right, so quick agenda, what I'm going to be talking about. I will do a brief introduction of what's the Kafka Streams for those of you who don't know. Kafka Streams is the framework that is embedded in Apache Kafka. You can use it for stream processing. Like if you're using Kafka and you do stream processing, you essentially get this out of the box. I will talk a little bit about how we scale apps and why this is important and what kind of things we solved in the Kafka Streams that help you to scale your application more efficiently. We're going to be going some of the one-on-one aspects of Kubernetes, but again, I know we're experts here in Kubernetes. I just want to point out some of the aspects of Kubernetes that's important for this type of application, of stateful applications. Plus, I will go ahead and some of the recommendations how you can do speed up of your the processing of your application, how you can do scaling, and how to do application recovery more fast and more efficient. All right, so the code from this presentation is available on GitHub. This is the QR code if you will use your iPhone or any other device. I don't know because I have on the iPhone, never use anything else. It will scan this and it will give you to link to GitHub, or you can just use a short link. It will find the playbook for the demo and all things that you need to know after I'm done talking. All right, so let's do a brief survey here. How many people deploying these days stateless application? Microservices, web apps, any type of stateless application? Keep your hands up. Who thinks it's a good idea? So keep your hands up if you, yeah, it sounds legit, right? So nothing prevents you from doing this, because state is somewhere else, right? So there's somewhere else like database or maybe cache or maybe something else there. But what about stateful applications? How many of you deploying any type of databases, any type of applications that require state? Maybe messaging queues, maybe databases, something like that in Kubernetes today. Keep your hands up. Who thinks it's a good idea? All right, so not many of you think that's a good idea. So let's see why. It's very, very, you cannot just simply do any talks about Kubernetes without mentioning or bringing some sort of quotes from Kelsey Hightower. And one of the things he known a couple of years ago, he mentioned that even though the Kubernetes has things that allows you deploy the stateful workloads into Kubernetes. Probably even Kelsey Hightower said, probably I'm not going to do this. But the interesting thing that he also tweeting with threads. So a lot of wisdom is actually somewhere down below. And another thing that he mentioned here is that the Kubernetes as a tool or as a platform can meet you only halfway, meaning that there's something needs to be done on side of things to understanding how specific tools, specific like Kafka or Kafka Streams application or database or Postgres or MySQL or Mongo, how these things need to work with Kubernetes. And specifically, this something is usually knowledge of SRE or engineer who supports this infrastructure and knows bits and bytes how to perform certain operations. So even though there are building blocks that allow you to build these systems on Kubernetes, you still need to have a pretty good experience of running this type of applications in general, and after that translate this knowledge into the world of Kubernetes. There's different ways how do people automate this, starting from the consultancy firms, and they just like simply shipping people to you that know how to manage this, to automating the things. There's very popular pattern called operator that essentially specifies the way how you automate this knowledge and introduce some of the custom resources in your Kubernetes cluster in order to make this tool more native to your environment, right? So you can have operator for Prometheus, which is database. You can have operator for Kafka, which is all things. It's a messaging system. It's a storage, persistent storage. It's the distributed system that requires some replication things. So the operator pattern is very popular. So, but this operator pattern requires someone to implement this knowledge. So now I want to give you a brief introduction how the things look like from perspective of developer who's dealing with the stream processing applications, namely with Kafka Streams. So everything starts with Kafka. Kafka is a foundational aspect of the thing. So Kafka is a event streaming platform that allows you to bring data in from different sources, make them flow through the Kafka. And after that, you can do certain processing. So Kafka includes a component called Kafka Connect that allows you to build or just use connectors for different data sources. Like you need to bring data from change data capture log from Oracle database. You're using the Golden Gate connector to bring data into Kafka using Kafka Connect. You're not writing it. You just simply go into the Confluent Hub, it's confluent.io/hub, and get this connector into your Kafka installation. Once you do something with this data, and we will talk about how you would do something with this, you can also use Kafka Connect to get data out. So like you want to offload this data to Elasticsearch for further searching, full text searching capabilities, or you want to offload this to some sort of like data lake. HDFS or somewhere where you can have a longer storage, longer duration. You can use so-called sync connector that allows you to sync this data out of Kafka. Now, in between, when the data is inside this Kafka, we need to use something to perform our computation. In this particular case, you can use any tool. There's if you're using Spark, if you're using something like the Hadoop, all these things, they have integration with Kafka. So Kafka Streams is the native library that comes with Kafka, and you just, if you Java developer or Kotlin developer or Scala developer or any type of JVM developer, you can use this Kafka Streams thing, and it gives you some of the opinionated the concept that allows you to build this kind of application. It gives you idea how you can perform not only stateless stream processing, but also stateful stream processing. So what's the difference between stateless and stateful processing? When you have when you need to know result of the previous step of your computation in order to calculate current step, it's a stateful stream processing. You need to store the state. You're doing sum, you're doing counts or you're doing some sort of aggregation. You do things like grouping. In this case, you need to have some previous states, previous things to. We'll do some posing here for a camera. Yes, so we're using this, the Kafka Streams to do this stuff. So what's important? Where to store state? Usually it's a big question, like, okay, so can we just do this storage in some other database? How we manage consistency if we have a processing and storage somewhere that's like outside of our processing? So who manages this consistency? How it can be done? And we're going to be talking about all these things today. So essentially, I don't know how many of you can read the Java. Java generally very good aligned with English language because the half of Java uses words from English language, so it's pretty easy to read. So essentially, there's two concepts that are available in Kafka Streams that you need to know. It's a K-stream and K-table. K-stream represents essentially history or like a sequence of events. These events are immutable, so you're not changing those. You only can derive something. You can get some new result out of this. And K-table represents the current state. The very easy thing that allows you to understand what is K-stream versus K-table and how are they different. K-stream represents your ledger. If you have list of all transactions that happen in your bank account, like everything that happened. And K-table will represent the balance, only current state of your account. Again, you have a history of all operations that happens in your bank account. It's your stream of events. And K-table represents a state, the current state for particular ID. So the concept of K-stream is actually bound very well with the Kafka topic. Kafka topic, it's a sequence of keyed events. So each event can have each message can have a key and value. Key will be used to figure out what partition data will be stored. Again, it's all things for scalability and how this data will distribute using consistent hashing algorithm between how this data land on different partition, how we can scale this. It's very, very fascinating stuff. As always, because when we're talking about scalability, it's always fascinating stuff. Now, in Java, when we're dealing with this, the processing, we have this concept of K-stream, and this is how we start building our topology. Do we have any people with PhD or a master degree in the graph theory? Anyone? Okay, so I can probably play smart here. There's a concept called directed acyclic graph. Or DAG. So essentially DAG, it's nothing to do with graph theory, but it's just a name. This is the way how to, most of the data engineers or developers of the platform that allows you to perform any type of computation, design the system or processing logic. So essentially it's a directed acyclic graph because it has beginning and has end. It doesn't have loops, so in this case, you cannot stuck in the one node. It always goes from a source to sink, and this is pretty much it. And this is how you describe how your data goes through this topology and what happens with this data. So essentially, everything what we do with this API, we take a source data, we group it by key. After that, we want to create a window that allows us to have, let's just say, some boundaries on our unbounded source of data. When we have a stream, we don't know when data will end. And we usually, it's not a batch when the thing's already finished and you know how much data you have there. You don't know when the data will end, maybe never. So that's why, but still you need to have a result. And Windows is a way how you can define some of the boundaries for this infinite stream of data. So in this case, we have a grouped stream that define the window that will include 5 seconds, and it will include all the messages that arrive within 5 seconds. And we'll perform the next step of this computation. And also this window will be advanced by 1 second. So it will be creating multiple dimensions. First dimension is the group by key, and the second dimension it's the time dimension for our stream. Now, we can perform certain things. In this particular case, I want to aggregate data for particular trades. And also, I want to have this state stored somewhere. So this is why I'm using this thing called materialized as something. So And once we've done this aggregation, we can perform some of the bits of computation. So we have collected all the trades within a 5-second window, and after that, we're applying this function that called compute average price. So we take all trades that arrived into our stream within 5-second window, and after that, we computate average. And this is going to be happening every second within 5-second window. So it's going to be sliding with 1 second advance. And after that, result will be placed in Kafka. So again, interesting thing that you need to remember, Kafka Streams is always read from Kafka and writes to Kafka. It's not the best practice, and it's not, even though you can, I not allow you to do that. So next time you think that, okay, so I have this Java API, I probably can call some other web service or some maybe go to database from perform. You should not do that. It is, again, breaks consistency. You need to think about multiple things. You're trying to expand the transaction that runs inside here, even though it's not a real transaction. It's just some of the anyway, it's complicated. Do not try to invoke distributed other system outside of the context of Kafka Streams application. If you need to bring data that, that data available on a different system using Kafka Connect to bring data inside the Kafka, and after that using Kafka Streams to join this data. It's a more advanced topic. I will be likely to explore this while we go into expert zone. Now, how it looks like from perspective of what it translates to. Remember I mentioned about this DAG, this direct acyclic graph. The direct acyclic graph we use in Kafka Streams to define this topology. So everything that we define in this DSL and the Fluent API, it's actually will be translated into a thing called processor API. It's a low-level API that allows you to define this topology, and each node will have a certain name. So when we start from beginning, when we're reading data from Kafka topic and we're writing data in Kafka topic, it will have two nodes. One is a sync node. This is how data will arrive into our topology. And another node is a sync node, how the data will how the data will depart from our topology. And after that, we have our processor nodes here. And remember, I mentioned the two types of stream processing operations, so stateless and stateful. So stateless operation here, operation like a map, right? It doesn't require you to remember what happened before. Because like you do things like in map, in map type of function, you do just a simple transformation, you change from one format to another. You don't need to have a past. You don't need to have a state from the past. And the second one, this is interesting. This is where we actually performing some of the state-based things. So first of all, now we need to remember about windows, we need to remember about time, and we need to remember this aggregated value. So this is why in our processor node that we're responsible for the grouping, windowing, and the other things, we have this state store. These small things here, over here, small database looking thing, will be responsible for storing the state. Now, how we scale Kafka Streams application. So let me talk a little bit about birds. Anyone watching the fascinating videos from National Geographic? And I like this. It just gives more expressive way how I can get into your brains, and you're never gonna forget this picture, and you will be always remember how the Kafka and the Kafka consumers will scale. Let me explain how it works. So imagine you have a mammy bird that brings these worms to baby birds. And these baby birds will constantly asking for more worms. So in this case, mommy bird will feed these worms into the baby birds. It will distribute those evenly across these beautiful birds. And if we will have another baby bird hatched, so in this case, mommy bird will perform this rebalance procedure, so it also will distribute these partitions or these baby birds. I already go a little bit further. Distribute these worms between multiple baby birds. So the way how it looks like in Kafka world, there's a component called consumer group controller that runs inside the Kafka broker. And this is a component that will be responsible for handling state of the consumer groups. When application reads data from Kafka, this application forms a thing called consumer group. And in our particular case, Our consumer group is actually a nest. This is where our consumers, aka baby birds, will be placed. So the way how it looks like, you have one consumer per application. You start application. This is required parameter that you need to specify in your application called consumer group ID or group ID. We have a mommy bird has 10 worms, and we have only one baby bird hatched out of this egg. Now all 10 worms, aka partitions, that our topic will consist of, will be routed to this the baby bird. So all these 10 worms will be fed to this the baby bird. Now, in order to increase consumption and speed up consumption and like increase this like a level of parallelism, we will bring few more baby birds into play. They will hatch out of their eggs, and after that they will perform the consumption from this topic 3 times faster. Right, so mommy bird will be responsible for distribute this partition evenly. So it's going to be like 3, 3, 4. 3 worms 1, 3 worms number 2, and the 4 number 3. What's going to happen if one of the baby birds will fall off the nest? Mommy bird will be responsible for taking everything from these baby birds, and after that redistribute this partition again. So this is in a nutshell how the Kafka handles, how it scales when you need to do read some data from Kafka. Less exciting picture, like as we engineers prefer to see. We have an input topic. The topic consists of the partitions. This partition can be distributed across multiple brokers. It can be distributed across multiple nodes. And for each individual input topic, the Kafka stream will create this thing called task. So each task will represent this small piece of this topology that will be executed. So essentially, each individual task that we run inside that represents our topology will be executed based on the number of partitions in these topics. So if we have 16 partitions, it will be 16 tasks. Tasks themselves, it's the way how the Kafka streams design a concurrency. So in this case, it not necessarily will be mapped one-to-one to threads or number of processors. There's a formula that allows to configure number of threads and how many tasks will be handled by different threads. And interesting thing from perspective of consistency, from perspective of concurrency control, these tasks are independent. So data from different partitions will end up on a particular task. So, interesting difference that people don't realize when they start using these stream processing systems is that it's not batch. So this is why you're not applying computation for a full set of data. Your message will go through this topology from source node to processor node to another processor node, and so far and so on, until it reaches the point where, let me see if I actually connected to the right thing, until it reaches the point where the data will be passed to the sync node, and from the sync node, it will land in Kafka. So now, when we computing this topology, when we're computing this, when our message will go through the things, and remember there was a small database that will be exist for one of the processor nodes. So this small database actually will be available per task. So in this case, each individual partition will have its own, or like an individual task will have its own instance of the small database. Again, why it's done, the way it's done, again, to prevent some of the things that involve some of the race conditions, some of the concurrency control. So in this case, they not share anything. So they not share any other state. So that's why we don't need to worry about concurrency control here. Now, with these things, you might ask, okay, so what's going to happen if application crashes? So we have this application that runs multiple tasks, and each individual task will be responsible for, like, not responsible, but will have this own, like, a state store and things like that. What's going to happen if application will crash? So this state store is the persistent storage. It's the small database called RocksDB, and this stuff will be stored in files on file system, but it's not maybe enough for us to perform this kind of things. So now, and we as the engineers will start thinking, okay, so now when application will just temporarily will go down, it will restart, it will read the store from the local file system, but what happens if this application actually died and, like, you lost the node? And this is normal situation when we run this in the containers, because we don't know where our stuff is running. Yes, so the things like the things like the container management software, all sorts of orchestration software, they will be responsible for scheduling our application, and we don't know. We don't have a control. So that's why we cannot say, okay, so it's going to be on files, but where's my files, right? And files might be on this node right now, but it will be rescheduled, and it will be available on a different node, so far and so on. Now, to solve this problem, engineers will start thinking, okay, so we already went here. So yeah, we've already been here. We go in here, how it's performed. You already learned a little bit about this. This is how I was talking about scalability, how this application will be scaling, how this task will be rescheduled on other instances. Now, this is where a world is perfect. We have rainbows and unicorns, everything works fine. Now we need to talk about the failures, right? When the things, when the software dies. So essentially, it's like once we solve the problem with the fault-tolerant state thing, we need to solve like the backward the problem. Like how can we survive the failures, right? One of the applications will die. So interesting aspect. So the application themselves, they will be able to manage where this task will be scheduled, again, through this consumer group controller that's stored in the Kafka broker. This guy will be responsible for rescheduling these things. And interesting thing that you might notice here, it is not just over here. It is not just the artifact that I forgot when I was moving this the animation from one place to another. It's actually how this data will be stored. So once the task will be moved from one instance, it will not remove the local state. So in this case, when this old task will be rescheduled here, the state will be also will be available, and it will be just little bit take less time to catch up and to recover. So the way how it works also. The engineers of Kafka Streams think, okay, so we're using Kafka for dealing with we're getting data in and getting data out. How about we use Kafka also to do state replication? So in this case, we're not introducing new databases. We don't need to have anything, and we already have a Kafka that brings data in, brings data out. We already have Kafka, so we don't need to introduce any new things here. So that's why the Kafka Streams uses this concept of changelog topic that will use this the topic to replicate all the events that happen in the local state, local store. The way how it looks like, again, we have these 4 tasks that our application is running. Changelog topic will have a same number of partitions that input topic and output topic. So in this case, each individual task will replicate its own state through this changelog topic. And this is how the data will end up on another application. So when you start new application, it will take this some time to rebalance and recover data from the Kafka. If before that some previous state was available, in this case the application only required deliver only delta. So you don't need to have full-blown state. Depends on the size of the application, depends on the size of your state. It might take a very long time. All right, so for recovery, what we need to do. So changelog is compacted. What does it mean? it means that it doesn't need to have a whole history. It only will have a delta, it will have a latest and greatest value, because this is only state that we will changing. So we don't need to have a history, because all the history already stored in the source and in the source topic. So if we need to replay whole history, we can replay this from the source topic and restart this topology, reset application state, and replay everything. For obvious reasons, the size of this topic will really depends on the size of the state that we'll be placing into these topics. If we have a large state and we have a big state and the compaction is not configured the way how it can be like very aggressive and just do like compaction very often, large state will apply very longer recovery time. So for Kubernetes fundamentals, I will skip that because we don't really need all these things. Only things that we need is only important thing that I need to remind you is the stateful sets, because stateful sets provide few interesting things that we need to have in our application. So because application will be using this RocksDB and storing data, so it will need to have persistent volumes. So we will use persistent volumes to store the data, and if application instance needs to be rescheduled somewhere else, this state will be reattached from the previous instance of application. If we killed pod number 0 and we reschedule this pod number 0 somewhere else, the persistent volume will be attached to this pod. And also, we will have a stateful network identity. It would be very easy for us to identify which application we're running on and what instance of application we're running. All right, so let's see if I still will be able to perform any demos. So I have this small cluster that runs my Kafka Streams application, 3 nodes. I'm not running Kafka in this Kubernetes. I will be using this the Confluent Cloud for that. And my application is essentially Java application that does one interesting thing. I have 2 topics. One topic will contain information about movies. I love movies, and information about ratings. So I want to get, using this Kafka Streams application, I want to have a scalable streaming rating processing system. I want to get the result where I have a movie and constantly updating rating of this movie based on these new ratings that coming from the from internet somewhere, because everyone has opinion these days and everyone is a movie critic these days. So interesting aspect here. So we need to do a few things. So we're getting this data in a very enterprise format. This enterprise format looks like the comma separated text. Let me show you real quick. And it's my data folder that has format like this. So one line represents one movie, and I'm using this double the columns to represent the separator. Pipes I will be using to separate individual actors or individual directors, and so far and so on. And the ratings also come in very enterprise format, something like this. It just has a movie ID and rating. So nothing not super difficult. So we need to perform a couple things here. We need to parse this movie to turn this into Java object. We need to calculate average rating. So in this case, we need to count rating for a particular movie. And after that, we need to perform sum. And after that, we need to do running average. It's just sum divided by number of ratings. And after that, we just need to join 2 streams. One will contain information about movies. Technically, it's a table because movie information on movies don't need to have a whole history. So in this case, it's going to be stored in a table. And after that, we will be constantly updating result that will include our streaming rating data. So in order to do that, I will start with small first application that will not require any magic from our side. So the way how it works, it's just a simple deployment that I will be deploying in my Kubernetes cluster. So this to build this Docker image, I'm using this tool called JIB or JIB. It's the Google open source this set of tools that allows to build the containers, and it fits very well in Java application. You just literally turning off your brain and don't even think how to deal with containers. So the way how it looks like in my, I use Gradle, and in my build.gradle file, this is how my container build looks like. So this is my project that contains my Java app, and this is the name of the container that I want to build. I'm using this Artifactory cloud to obviously to deploy my repositories. Jib actually works with any container registry. For certain container registry, it will require some of the credential helper. So if you're running this in the GCP, for example, in GCP it will require certain specific the helper to do container registry. Also, I can specify the image that the base image for my application. This base image essentially will not include anything except just the Java runtime, and after that it will give me a very slim version of my application. So I'm gonna go ahead and just go Kubernetes, and I'll just do key create movie ratings. So it goes here, start with one container, and if I will do key logs, true, let's see the pod, and I will also want to follow. And what I will see here, most important thing here is errors, obviously. No, not necessarily. Something is not right, maybe. Something broken. Okay, topic replication factor must be 3. All right, so in this case, like the way how are we doing this on the live demo, stream with demo. So we will do things. So this is why you need to put these important configuration parameters outside of the scope of your application. Now, so in this case, I will just do jib. I'm building this stuff. I am in the wrong directory. I will go out. I will just do, so this way how it looks like, Gradle build jib, Gradle W. So what it will do, it will recompile my application. It will grabs this stuff as a result of this application. It will pushes this into my Artifactory. So my Artifactory is over here. I have my Docker registry, and obviously I'm using this latest tag da. This is the only way how you do it. No, seriously though, you don't need to do this. You know, the version, your application, the follow release cycle, and things like that, because just this stuff only works well on the live demo. Now, so while it's doing this, my application went into KDEL streams rating. So I'm removing this deployment, so my container will die. While it's doing, I can redeploy this again. I'll do key create. I'll do deployment once again. Okay, I'm going to different directory as usual. And let's do deployment, container creating. Let's see if we don't have any errors. Where's my logs? Because the pod is changed, so a lot of interesting stuff is going on. All right, application is up and running. Yeah. So the thing is that when the application will be running, we can start populating some data. In this particular case, I need to pull this initial data. In this case, I'll do cloud produce. I produce my raw movies. They will land in this topic, and after that, I will put some of the Gradle W. I have this generator that will just write some nonsense ratings that will emulate the real world scenario where the people would put ratings on the internet. And how I will see that this actually works, I can go here. It calculates something. I see it's in logs, but also I want to consume this from the topic. So the Kafka puts stuff, the result of this computation, puts in another topic. So see, some of the data goes into thing, and some of the some of the results you will see it twice, but it's just the way how the terminal represents the streaming data these days. So now what I can do here from this, I can do scale, deployment, deployment name, replicas, and replicas too. So in this case, this is how I scale my application. It's up and running, so far and so on. I can do this, say, okay, I can do it 4 because I have 16 topics, but we will quickly see they will stuck in this kind of state. Usually I would love to discover this kind of thing with people, so they will suggest something or like troubleshoot something, but we're running out of time. So for deployment here, I'm also specifying affinity policy. So in this case, 2 instances of application, they will not land on the same pod because it's the, you want to have dedicated instance for your computation thing, and if one of the nodes will go down, you don't have multiple instances of your application go down. I just do scale 1. One of the options is just to DLD streams rating. So I will remove this deployment. So second thing is that I'm leveraging stateful sets. So for the stateful sets, I'm specifying a location where I'm storing this data, in this particular case, where the Kafka streams will find this place. And after that, a persistent volume will provide me with these stateful. So with this option, the first option for the replication of the state, I'm relying on Kafka. In this case, I'm relying on Kafka Streams. So very encouraging, very funny pictures at the end, so you will understand what's the difference. So some people think the stateful sets are complicated. Some people don't need to use them, but they make things faster because they allow to just simply reattach the storage from one place to another. If we need to do something like only stateless stream processing, if we need to do filtering, if we need to do any transformation, we don't need to have a state. We don't need to use these resources. So it's going to be with just scaling up and down, and we're fine with that. And also, sometimes you just simply don't trust. You work in the company with the hostile environment, very toxic environment, and you don't trust you don't do DevOps and things like that. And hopefully, it's not the people in this room. And you don't know like what to do with this stuff. So one of the last slide that I'm showing that for recovery state, it was an example of the Kafka streams, but some of other applications have a very similar properties. If you're relying on some sort of like embedded database, or you're relying on some sort of storage when you're writing small files, or so far and so on, the ability to recover state from multiple places, like from Kafka, if it's not very big, so it will not take your application a very long time. Kubernetes makes it very easy to scale this application. So just go in there. I can also go and scale my stateful set, and I can provide 4 replicas here, and it will just fire up in other instances. Kubernetes is known for the name of the Greek god that responsible for you spending money on your cloud bills. This is how you do your scale and how you spend your money. Thank you so much for your time. Sorry for quick setback. Some of the resources, if you have any questions, I'm always available in Twitter, and I will be available for advanced interrogation after the session. Thank you for your time.